Lesson 64, derivative world today. Derivatives of inverse trig functions. What'd you say?
It seems like we've been in derivative world forever.
We bounce back and forth.
All year.
Not all year, but we've done a lot with derivatives, but we also throw in integrals, so.
Those are pretty much derivatives.
As long as you know they're backwards. As long as you know they're backwards, that's the key. Okay, so, as we look at these, you are basically being given, right here at the top, the derivatives of the 6 inverse trig functions. So, we've got our sine, cosine, tangent. Now notice, this isn't the derivative of sine, cosine, tangent. This is derivative of the inverse function. Okay, so sine inverse, cosine inverse, tangent inverse, and also the derivatives of cotangent inverse, secant inverse, and cosecant inverse. Okay, what we're going to spend a little bit of time doing today is going through and figuring out how to derive these. In other words, in a technical sense, if you forget one of the derivatives, you need to know how you can go through and find it. Okay. When we talk about what to memorize, if I recall, I think it's sine and tangent. Yeah, sine inverse and tangent inverse are the two that are probably used the most. And you need to be able to use and to recognize. Okay? So, let's go ahead and look at example 1. And then we can talk about how it all pairs up in a moment. Example 1, first of all, it says y equals arc sine of x over a. Find y prime. First of all, realize, what's another way to write arc sine? Yeah, that is the sine inverse of x over a. Old news, right? But just a reminder, when you see arc sine or if you see sine inverse, those are equivalent. So whichever one your brain goes to, recognize them as equals. Now, my job is to find y prime. Ignoring this up here, do we know the derivative of sine inverse? No, and it's not at all like taking the derivative of sine as cosine. Totally different. Okay? So, what we're going to do is, as I said, we're going to try and figure it out. First of all, what do you know about an inverse? In order to take the inverse, what do we do? Not thinking derivatives. I think I asked this a bad way. I want to ask it a different way. Okay. My brain's sputtering for a moment. Bear with me. If I say sine of x equals square root of 3 over 2. How can I plug that? What can I use to plug that into my calculator? What? Yeah. You can use the idea that this then is going to be x equals, he said arc sine, I'm going to write sine inverse of square root of 3 over 2. So my point here, what I'm trying to get you guys to remember, is that to go between, if you have sine here, to get the sine inverse, what happens? These pieces switch, right? The x and the square root of 3 over 2 switch, because that's what the sine inverse does, it switches the pieces. So here, if we have sine inverse, how do you get over to sine? You're going to switch the pieces. And that's what I'm trying to suggest here. And so if we have y equals sine inverse of x over a, sine of, what are we doing there? If you flip them, we're going to say, I don't want to use marker there. Okay. If I flip them and get it out of sine inverse, we're going to say the sine of y equals x over a. In other words, just switching those pieces. So sine of y equals x over a. That's how we get back and forth between sine inverse and sine. Sound a little familiar?
Little.
We did it last year. I promise we did. I can't guarantee how much we've done this year, but
This is sparking.
okay.
Something like this was on.
It wouldn't surprise me. You know how Saxon is. Okay, so we can't really, it was in y equals form, but we couldn't take that derivative. So now let's differentiate this both sides. So we'll use differentials. Okay, it's like the dx's and dy's. So what is the derivative of sine y? Derivative of sine of something is cosine of something. So cosine y, because this variable is a y, we're going to say cosine y dy equals, what is the derivative of x over a? Now keep in mind, a is like a number. Okay, a is like a number. And so, if you think of a, think of this, you could think of this like x over 2. Just, you guys work better with numbers. I know I do at least. If we think of this as x over 2, that's really, you agree that x over 2 is 1/2 x? So x over a is 1 over ax? 1 over a times x, that is. So what's the derivative of either of these? What's the derivative of 1/2 x? Just 1/2? What's the derivative of 1 over a times x? 1 over a. And then because, so derivative of x over a then is 1 over a. The variable was an x, so we're going to say times dx. Now, if we're trying to find y prime, we're going to solve. What do we want to try and solve for? What's the equivalence of y prime? dy over dx. So can you solve this and make it dy over dx? If it's dy over dx, we're going to keep the dy, divide the dx over, and then what else has to happen? To get the cosine y over, we're going to have to divide it over. So I'm going to write it as, there's already a 1 over a, right? And then a 1 over cosine y. Now, here's the problem. I'm just trying to get a better form. Okay. Yes, it would be. I mean, in all technicality, it is 1 over a divided by cosine y. However, when you divide, so 1 over a divided by cosine y, if you change it to multiplication, it's 1 over a times, what's the reciprocal of cosine y?
I actually followed that.
Okay, so it was just an idea of, I definitely don't want to write a fraction within a fraction. Yuck, ugly. So if you're dividing by cosine y, it's the same as multiplying by 1 over cosine y. That's the direction I was going there. Are we okay with that now?
Would we be able to do a negative 1 over cosine y, or would that leave that same thing?
We don't want to in this case. It's not that you can't go with the idea of, I know where I'm going with this, and so in this case, I don't want to. I agree it is a to negative 1, that kind of stuff, but yeah. Now, the problem we have here is we're finding y prime, or the derivative of y, but notice, what do we have in the problem? We still have a y in the problem, which you can't really have when you're finding y prime. Okay? So, we're going to use a triangle here. I'm going to set up a triangle based on this right here. Sine of y equals x over a. So, setting up a right triangle, because of course sine, cosine, tangent, those trig functions are all about right triangles. And it says sine of y is equal to x over a. So that means the sine of y is an angle. So I'm going to call y this angle right here. Okay, I'm calling y that angle right there. It could be the other angle that's not 90 degrees. X over a. Where does x go and where does a go? If sine of that angle is equal to x over a. Opposite over hypotenuse? Yes. So opposite is going to be x. Hypotenuse is going to be a. It could have been leading into it. No, it could have been. You could have been leading into it. Okay. Now. Okay. Well, see, Aubrey's agreeing with you, so you should hopefully have done the right assignment. Unless you guys both. Well, wait. Did you use Aubrey's pictures?
Did I use Aubrey's pictures? No.
Okay. So. You're probably okay, but you know how Saxon leads, okay? Saxon leads in. We'll find out later if you're on the right assignment or not. Okay, now, here's the deal. We need cosine of y, yes? What's cosine? Adjacent over hypotenuse. What's my catch? I don't have an adjacent. But it's a right triangle. How can I find that piece? Pythagorean theorem?
Yes.
Okay, if you can get to it without that, great. I don't know, what do I want to call question mark? So I'm going to...
They gave us those.
But x over a was given in the problem. So that's why I labeled this a.
But it's going to end up being C.
No, I'm not using C, I'm using the pieces they gave me.
This one seems really similar.
Okay, so here, I'm going to call this bottom piece B. Just, I don't know. B squared plus the other leg x squared equals a squared. So I'm trying to solve for B. B squared is a squared minus x squared. So what is B? The square root of a squared minus x squared. So what does that tell me? This adjacent side that I need down here is the square root of a squared minus x squared.
It was x over a equals sine y. I guess.
Which is what it's not what we started with, so that might have been leading you into it.
So there's not 15.
Okay.
Earlier, really early, the third problem into our homework assignment, did you get one of the graphs that we did at the very end of class yesterday? The table? Because that was I think number 3 or number 4. I know I did the right one because this is one that had the 25 split, and they said they were.
Yeah. Okay. Okay. So moving along here. We had dy dx equals 1 over a times 1 over cosine y. I want to replace cosine y. Can I find cosine y now that I've used Pythagorean theorem? Yeah, because we found using Pythagorean theorem, this third side is the square root of a squared minus x squared. So now, I'm going to rewrite this. Dy dx, it's still 1 over a, and it's 1 over cosine y. So what is the cosine of that angle? Adjacent over hypotenuse. So it's going to be the square root of a squared minus x squared over a. And yes, now I have a fraction within a fraction, but we're going to take care of that momentarily because I can't leave that for long. Are you okay?
Yeah, so I was thinking ahead.
Okay.
We're looking at the answers.
Oh, okay.
So, you know.
I heard Jack do an aha earlier, so I had a feeling he was looking ahead and saying, oh, I see where this comes from. Okay, guys, 1 divided by this fraction. What really happens? it flips. So 1 over this fraction, I can really just flip this fraction, and it's a over the square root of a squared minus x squared. And the reason I didn't want to use a to the negative 1 is my a's cancel. And so I have the derivative going to be dy dx is equal to 1 over the square root of a squared minus x squared.
Is this kind of like that problem that we had? It was in the final, it was like one of the first problems that we had, where it was like the fraction on the fraction on the fraction on the fraction. We just had to keep simplifying it up.
Yeah. I mean, it's just the idea when you do 1 divided by something, it's the same as 1 multiplying by the reciprocal. Okay, so notice, this was our sine inverse problem. The derivative of sine inverse, 1 over the square root of a squared minus x squared. If you look up above, it's in slightly different form because they have the dx up there, but it matches up, yes? Derivative of sine inverse of x over a is, if you want to think of it as 1 dx over the square root of a squared minus x squared. Okay? Did we follow that? Okay. So this next time it should be a little easier to repeat the process. Because now we've got to do the same thing with. Okay. So, repeat the process here, guys. This time we're starting with y equals arc cosine of x over a, and we want to find y prime. So, first of all, arc cosine is another way of saying what? Cosine inverse of x over a. How do I go from a cosine inverse to a cosine?
Switching the things around.
Switching your pieces, switching your input and output. So then I'm going to say cosine of y equals x over a. Now we're ready to take the derivative. Derivative of cosine of y. Negative sine y. We're working in, we need differential here, so it's times dy. Derivative of x over a. 1 over a, and then times your dx. Refer back to the board. And if you prefer to say dx over a, you can. Because I know, Jack, I think you said that earlier, so that's perfectly fine. Solve this and make it dy dx. So if I make it dy dx, 1 over a is going to stay. The dx I divide to the other side, and I need to divide the negative sine y. So I'm going to do the same thing as last time and say 1 divided by negative sine y. I can. Actually, I'm going to scooch it up. What's my problem at this point? I've got a y within my problem. I'm going to sketch another triangle over here. So right triangle, because we're talking trig. This time, I'm using my statement that cosine of y equals x over a to label. So cosine of y, so that means y is my angle. Cosine of y, what's my phrase for cosine? Adjacent over hypotenuse, so that's going to be x over a. This is the part I was going to kind of skip this time. Probably shouldn't do that. No, you're fine. You're fine. Okay. How do I find this third side? Pythagorean theorem. So x squared plus whatever you want to call this, question mark, right, is equal to a squared. And honestly, you could even say x squared plus question mark squared equals a squared. Can you agree with that statement? So I'm solving for this now. So I'm going to subtract over x squared. Question mark squared equals a squared minus x squared. Take the square root, right? So question mark is the square root of a squared minus x squared. That's just, you're just solving Pythagorean theorem, you just don't get a number answer. So this is the square root of a squared minus x squared. Does that help a little bit? I know I went through that kind of fast, but.
I think last time I just had I couldn't figure out where to put everything in the equation as far as the addition of that. And then
You guys were also distracted by last night's homework at that point, on that particular part too. Okay, dy dx. Still 1 over a, and this time it's 1 over what? It's negative sine y. So first of all, I need to put a negative. Sine of y. So what's sine? Opposite over hypotenuse, so it's that square root over a. So the negative of square root of a squared minus x squared over a. You've got 1 divided by a fraction, so that fraction can flip up like last time. So dy dx equals 1 over a times, I'm going to say the negative of a over the square root of a squared minus x squared. A's will cancel. And so now my derivative is the negative of 1 over the square root of a squared minus x squared. So what's the difference between sine inverse and cosine inverse derivatives? A negative sign, right? Other than that, it's all the same. Kind of similar. Well, no. Okay. One more. No, we have one more. Well, we'll see when we get to the back. Let's do tangent inverse. Tangent is an important one. Okay. So notice this one. It already says tangent inverse of x over a. So I don't have to worry about going from arc sine. So how do I get from tangent inverse to tangent? Tangent of y is going to equal x over a. Derivative of tangent. Secant squared. So secant squared of y times dy. The derivative of x over a. 1 over a times dx. I'm going a little faster this time. Holler at me if I can't. We need to solve. Make it dy dx. Keep the dy. Divide by dx. 1 over a stays. And then we're dividing by secant squared. So it's 1 divided by secant squared of y. Thoughts on secant squared of y being in the denominator? Okay, so we still have the issue of it can't have a y in there, but not what I was going for this time. What is 1 divided by secant? 1 over secant. Secant is the reciprocal of cosine, yes? So 1 over secant squared is the same thing as saying just cosine. or cosine squared, that is. So, my point is this time, since it was 1 divided by secant squared, the reciprocal of secant is cosine, so that's just a cosine squared. Okay. Again, what Wade said, I've got the y issue, yes? So I'm going to set up my triangle again. This time my triangle is based on the idea that tangent of y equals x over a. What do we know about tangent? Opposite over adjacent. Can you do that Pythagorean theorem in your head? It's going to be question mark squared equals a squared plus x squared. So all you have to do is do square root of a squared plus x squared. Actually, okay, they write it as a squared plus x squared over there. I sometimes write it as x squared plus a squared, so fill it in. dy dx is equal to 1 over a times cosine squared. So that means you need to find cosine and square it. So what is the cosine of y according to my triangle? Okay. A over square root of a squared plus x squared is cosine. Since it's cosine squared, I have a square on that fraction. I guess I didn't, oh well. And so what happens when you square that fraction? The denominator, when you square that square root, just becomes a squared over x, a squared plus x squared. A on top will become a squared, but one of those a's will cancel with the a in the denominator. Final answer? A over a squared plus x squared? No square root this time. So your sine and cosine have the square root. Tangent does not. Okay. I'm going to temporarily skip example 64.4 because to me it's more important that we get through and understand the bottom part because that's what you're going to be using on a regular basis. Okay. Example 4 is what? Just showing how you can find cosecant inverse. Okay. If we have time or if you guys really want to, we will make sure to come back. But to me, the bottom section is more important. Now, derivatives of inverse sine and inverse tangent appear more frequently. So it's a good idea to memorize those two. Okay. Notice the form when they give this. It's sine inverse. Notice how it is x over a. So if it just says sine inverse of x, realize that a is just like an invisible 1. And then think of this, sine inverse of x over a. What's on top with the dx? Just a 1. So like we found in the front, the derivative of sine inverse of x over a is really the part you have to be concerned about, 1 over square root of a squared minus x squared. Tangent inverse, it's sine inverse of x over a. Notice there's an a on top. It's a over a squared plus x squared. We found those on top. I don't know if those circles help or if they don't, but I found some confusion in the past years with that dx up there. So, okay. Ready to try these? This is using our rules now. If y equals tan inverse of cosine x, what is dy dx? Okay. Okay, well, so we're being asked, what is the derivative of tan inverse of something? What is the derivative of tan inverse of something? We look up here, it's a over a squared plus x squared. The catch is, what is a and what is x? Yep, I agree. So here's what I think. If you think x over a, where is x over a in place of? It's the inside pieces, yes? So this part right here, that's my x over a. What is cosine x as a fraction? Cosine over 1. So think of x over a as cosine x over 1. Meaning, if you have an x in the definition of derivative, we're going to say cosine x. If we have an a in this case is just a 1. So here, if you follow the definition of tangent inverse of something is a. What is my a value in this case? In other words, what is the denominator? And that is 1 over a squared plus x squared. So a squared is going to be 1 squared plus x squared. What was my variable in this case? Or what was my numerator? Cosine x. So we're going to say cosine squared x. Now, when we do the derivative of something, derivative of tangent inverse of something is that a over a squared plus x squared, and then what do we have to still consider? Chain rule. Derivative of the inside. What was in position of x? In position of x was cosine. So you now have to do the derivative of cosine x. What's the derivative of cosine x? Negative sine x. So that negative sine x right there is a result of chain rule. Anytime you're in your variable something other than just a 1x, can you take the derivative of it? Okay, at this point, it's a matter of cleanup. I don't know if Wade figured anything out. He was trying so hard I could tell to use a Pythagorean identity, weren't you? At least I was guessing.
Not on this one. I was earlier.
Okay. 1 squared is 1, right? 1 plus cosine squared? Well, if it was 1 minus cosine squared, we could talk about Pythagorean identity.
That wouldn't matter.
But we can't here, so all you can do is just make this a fraction. dy dx. If I multiply 1 times negative sine x, that's going to be negative sine x. I can say that 1 squared is 1 plus cosine squared x. If there was an identity or something that could simplify something, yes, by all means take it. But there's not here.
Hey, look, that's cosine squared, or that's sine squared.
It looked like you were trying to do that, so.
That would, if we had that on our test, that's so would have gotten me. The 1 plus cosine squared x. I would have tried to make it into the identity.
You have to watch the signs. Okay, let's try example 6. Y equals arc sine of 2x. Find y prime. So realize arc sine is the same thing as saying sine inverse of 2x, yes?
Yes.
Now, before you get started, what's x over a?
2x over 1.
Okay, so you realize there's like an invisible 1 here, yes? And so when I think about x over a, I'm thinking about 2x over 1. So every place in my definition I see x, I'm going to put in 2x. Every place I see an a, it's still just a 1. So what's the derivative of sine inverse of something? If you look up top, derivative of sine inverse of something is what? 1 over the square root of a squared minus x squared. What's my a? What's my denominator? 1. So that's just a 1 squared minus x squared. What's my numerator of that fraction? 2x. So 2x quantity squared times, can I take the derivative of what was in my x spot?
That square is inside the square root,
It is. It's on the 2x, yes. So what did we put in place of x? We had a 2x. Can we take the derivative of 2x? Derivative of 2x is 2. So, clean this up. And that's as far as you can go there. So I'll put it over here. So y prime is that 2 I'm going to put in the numerator. Square root of 1 squared is 1 minus 2x quantity squared could be rewritten as 4x squared. I think I need to turn the volume down on my computer or the TV, one of the two. Okay, one last one. All day today has been derivatives. Now we have an integral.
Oh, but why only 1?
So it is. Now think about it. We've been learning all these derivatives. They're trying to start training you about recognizing integrals. Because this is one of the things with inverse trig functions you just have to recognize. So the integral of 1 over 1 plus x squared dx. We don't really have a method to integrate this because they want you to just recognize this. Which derivative have we learned today that this matches the answer of? This is a tangent inverse problem. Okay? And again, this is one of those you have to recognize, you have to learn to recognize the form. Thank you, my dear. And so, if you notice, what is it? Tangent and cotangent are the ones that do not have square roots. Cotangent has a negative. This guy's not going to have a negative. And so, you have to learn to recognize that, 1 over 1 plus x squared, that is going to have something to do with tangent inverse. And so if you look up above, the derivative of tangent inverse of x is 1 over 1 plus x squared, if you think about it. I should have said that differently. Derivative of tangent inverse. If you think of that as x over a, what's my a value? And the invisible 1, right? And so if a is that invisible 1, then that means this is a 1 on top and this is a 1 here, where it would be a and a squared. So what do you know? If the derivative of tangent inverse is 1 over 1 plus x squared, what's the integral of 1 over 1 plus x squared? It's obvious. Tangent inverse x plus c. So the integral of 1 over 1 plus x squared dx is equal to tangent inverse of x plus c. If you were to try and go and actually integrate this, you wouldn't have a lot of luck. Because we don't have, if you try and do like a guess and check or a use substitution, we would need a chain rule thing because the derivative of x squared is 2x. There's no 2x in there. So I'd run into a roadblock. And so it comes down to you just have to, that's why another reason to memorize sine inverse and tangent inverse derivatives. Okay? Another thing to add to the calculus memory bank. We've got 10 minutes. Can we get some homework checked? Or do you want me to go back and do example 4?
I'm good with either one.
I think I just as soon get some homework checked.
Do you have that Patrick that was in?
Huh?
Got 2 days.
Got 2 days.
Yes, yeah. Yeah, I know. That's another reason I'd rather get some homework checked because